Hello everyone, welcome to Technologies Discussion channel. Today, I'd like to continue the discussion on filter design. Okay, there are actually two parts for today's discussion. Okay, the first portion, okay, I will discuss the key difference between pseudo-Combline and also Combline bandpass filter. So this will be the first objective, is to highlight the key difference between these two types of bandpass filter, pseudo-Combline and also Combline bandpass filter. Next, okay, I will share with you how can we actually design a pseudo-Combline bandpass filter. Okay, the method to design this Pseudo-Combline bandpass filter is actually quite similar with the Combline bandpass filter, which I have did on the part 35 series discussion. Okay, but all this will be the discussion for this video. This will be the part 36 series discussion on filter design. So guys, if you're keen to know more about filter design, okay, please take a look on the playlist under the description. Over there, you will be able to find a series of discussion on filter design. This is my email. If you have any question regards on this discussion, okay, please drop me an email. Okay, or if not, if you want to have a faster response, you are also welcome to ask me your question through the comment. Before I continue, okay, I'd like to urge you guys to help this channel by like this video. Just spend a few seconds to press the like button now. For those who are new to this channel, please consider to subscribe and turn on your notification bell. Once again, thank you so much for your strong support. Let's quickly do a quick comparison, okay, between the Pseudo-Combline and also the Combline filter. Okay, so this method, okay, designed by Pseudo-Combline and also Combline actually filters, they are actually mainly used to design bandpass filter. Okay, they are all based on the principle of resonator coupled together to achieve the desired filtering characteristics. However, there are key difference in their design and also their application. Okay, so in short, for Combline filter, in terms of structure, they actually consist of multiple short circuit resonator, okay, typically transmission line arranged in parallel. Okay, so this is actually a so-called the structure of Combline filter. Okay, you can see that they are actually so-called a parallel resonator. Okay, they are actually all shorted over here. Okay, so basically this will be for the Combline filter. As for Pseudo-Combline filter, you can see that they are actually all open circuit, okay, on this end here. So this is the first difference. Okay, for Combline, okay, on this side here, they are all short circuit. But for Pseudo-Combline filter, these are all open circuit. Okay, so let's take a look. On another one, the resonator are often loaded with capacitor to reduce their physical size. Okay, so you can see here, this is what it means. So they are actually loaded with capacitor, okay, so as to reduce their physical size. So which means that if we have this capacitor, the length can be shorter than lambda over 4. Okay, for this case here, for the Pseudo-Combline filter, is the same meaning. Okay, with the capacitor, the length can be also reduced, which we are going to discuss later on. Next, okay, on a Pseudo-Combline filter, okay, they are actually very similar to the Combline filter. Okay, as I show it to you, I think the key difference is on the end of this Pseudo-Combline filter, they are actually open circuit. As compared to Combline filter, they are actually all short circuit here. So basically, as what you mentioned here, they are the same with Combline filter, just having couple resonator, okay, but with distinct difference in coupling and resonant tuning, okay, which we are going to do with an example later on. Okay, so it often use technique like tighter coupling or different loading condition to achieve specific filter characteristic. Okay, so basically this is in terms of the structure, which I have highlight. Next, okay, in terms of the compact size, okay, so basically I have mentioned that when we actually add the capacitor at the open end, this actually can make the resonant length actually reduce. So therefore, you can see that with Combline, okay, you can see that the length of the transmission line is actually a quarter wavelength. So basically for Combline, okay, it's actually with a factor of quarter wavelength of transmission line. But for pseudo-combline, okay, the length of this transmission line, in fact, is half of wavelength, which means that they are actually double the size of the combline filter. Okay, so in short, okay, because of the length of the transmission line, pseudo-combline is actually having a larger size as when to compare to the other method, okay, which is the combline filter. Okay, however, it had clear distinct advantage. Okay, so basically we have some form of relaxed constraint, okay, on resonator dimension and also coupling element, okay, which means that we don't have so tight coupling effect, okay, for this pseudo-combline filter. And let's say we have some manufacturer deviation, okay, some error, let's say, okay, so instead of, let's say, 0.16, let's say, then basically the error is 0.18, then the effect won't be so drastic. Okay, so basically this is the advantage of having this pseudo-combline filter as compared to combline filter. However, the combline filter, firstly, they are so-called smaller and more compact. However, another disadvantage of combline filter is basically you can see that this part are all short circuit. Okay, let's say we fulfill this filter on a transmission line, then we need to have VR, which is the process can be quite tedious and the result cannot, can be quite different. So therefore, when we actually design with pseudo-combline filter, okay, we can actually control more parameters here. So hence, because of this, the result of the bandpass filter, okay, will be more desired as compared to the combline filter. Okay, so basically this is another key difference. Okay, next. Okay, so for combline, okay, this is a widely tunable. Okay, the resonant frequency can be adjusted by vary the capacitive loading. Okay, so basically we can control, okay, by the capacitive loading. Okay, so for combline filter is actually very high selective. Actually, pseudo-combline filter is also high selective. Okay, so on the last slides, okay, I will show a frequency response of the design of pseudo-combline filter. Okay, they are actually all quite high selective on the so-called on the upper side. Okay, so therefore for this, they actually provide very sharp filtering characteristics due to the strong coupling between resonator. As for pseudo-combline filter, okay, so what is the key features? Okay, so as I mentioned, you actually have some form of relaxed physical constraint. Okay, so the design actually allowed for easier implementation in some mechanical and electrical layout. Okay, so they actually has a lower sensitivity, okay, when we actually have some component tolerance. Okay, so basically this is the advantage of pseudo-combline filter design. Okay, so basically, as compared, they will be less sensitive to manufacturing variation. Okay, so next, okay, so this for application, okay, but they are actually widely used. Okay, so they are widely used in RF, microwave communication system, satellite system, and also radar. Okay, so they are suitable for medium to high Q. Okay, so basically for combline, mainly used for high Q requirement. As for pseudo, is basically for low Q, slightly low Q. Okay, so they are often used where a slightly larger footprint is acceptable. Okay, but manufacturing tolerance or design flexibility are priorities. They are suitable for applications that require moderate selective, okay, which means that they don't have so high Q and they are less stringent size constraint. Okay, so I think the key thing is when you actually can afford the size, then you consider to use this pseudo combline filter. But if not, we just fall on this combline filter to design our bandpass filter. Okay, so with this, I think you have a better idea the key difference between pseudo-combline and also combline filter. Okay, so now let's concentrate on the, so this is a table that highlight the key difference here. Okay, so I think I have mentioned enough on the key difference between pseudo-combline and also combline filter. Okay, so I just put everything over here, okay, to summarize all the discussion on the key difference. Okay, so let's take a close look on the pseudo-combline filter. Okay, so pseudo-combline bandpass filter, they actually comprise of an array of coupled resonator. As you can see over here, these are all resonator. So over here, you can see that there are actually an array of coupled resonator. The resonator consists of line element 1 to n. Okay, so basically the 1, okay, all the way to the n, these are all the resonator. Okay, so they are all the resonator which are open circuit at one end. Okay, so basically you can see that they are actually all open circuit at one end. Okay, and then on the other side, okay, basically they have this lump capacitor loaded between the other end of each resonator line elements and also the ground, which mentioned over here, which I have described earlier on. Okay, the filter use the tap line as the input and output. Okay, so basically this is the tap line. This is where the input, this is where the output. So basically later on you realize that we also need to design the location of the tap line. Okay, so basically this is what it means here. So the filter actually use the tap line as for the input and also for the output. Okay, with the lump capacitor present, okay, the resistor lines will be less than lambda over 2 long at resonance, where this lambda G0 is actually the guided wavelength in the median of propagation at the mid-band frequency of filter. Okay, so basically this is what I have highlighted early on. Okay, with the loading of capacitor, okay, the length can be further reduced, which means that you actually can have a shorter so-called length of the resonator, okay, if you design with a capacitor. At the mid-band frequency F0, okay, each open end of the lambda over 4 open circuit stubs actually reflects an electric short circuit on the other end, resulting in a virtual ground. Okay, so what does this mean? Okay, so basically, this is the meaning here. These are all open circuit. So when we actually travel on a Smith chart, a quarter wavelength, this part actually becomes short circuit. Okay, so basically in short, for this pseudo-Combline filter, on the end here, they are actually all open circuit. However, when the length of the transmission line is a quarter wavelength, this part here become a short circuit. So basically with this, you can imagine that this is actually very similar with the Combline filter design, because this is open circuit. When they come over here, these are all short circuit, but you can see that they are actually the same as Combline filter. So basically, in short, the key advantage of using this Pseudo-Combline filter is basically we can remove away the short circuit here. And then basically, based on the length of the transmission line, it become a virtual ground. And therefore, we have all these short circuit, which resemble exactly the same as Combline filter design. Okay, so basically, in short, whatever you design on the Combline filter, you actually can be used on this Pseudo-Combline filter. So basically, this is the meaning here. Okay, so therefore, the physical grounding of the resonator may be replaced with the virtual grounding produced by the array of the lambda over 4 open circuit stub. Okay, so basically this is exactly the meaning. Okay, so over here, this part belongs to here. You can see that they actually open circuit. Okay, once they travel quarter wavelength, all this become short circuit. So basically all this become short circuit. Then this whole filter design will be look very similar with Combline filter design. Okay, so this is actually for Pseudo-Combline filter design. This is actually for Combline filter design. So basically, you see the similarity between these two. Okay, similar to the Combline filter, if the capacitor were not present, okay, the resonant lines will be a full half of wavelength long at resonance, and at the filter structure will not have any passband at all when we actually realize this in strip line, okay, due to the total cancellation of electric and magnetic coupling. Okay, so basically this will be the case if we use this method to design on a strip line. However, for microstrip realization, this will not be the case, which means that for microstrip design, you still have the bandpass filter. Okay, so basically all this design, if you fulfill in strip line, then you will not have the bandpass filter. However, as I explained earlier on the Combline filter, if we fulfill this design on the microstrip line, then we still have this so-called bandpass filter. Okay, so basically this is actually the formula, okay, for Combline filter. Okay, so basically they are the same for Pseudo-Combline filter as I highlighted earlier on. The key thing is basically the transformation from open circuit to short circuit. So how we calculate is almost exactly the same as Combline filter. But let me give you an example, okay, how we actually can design this Pseudo-Combline filter. Okay, but before we go into the example, guys, again, I urge you to help this channel by like this video. Okay, when more of you guys actually like this video will have a better chances to reach out to a larger audience. So guys, I'd like to urge you guys to help this channel by press the like button now. For those who have learned something, okay, please if you are also new, please consider to subscribe and turn on your notification bell. Okay, so once again, thank you so much. Let's come to the design of this Pseudo-Combline filter here. Okay, so basically this is the example. Okay, basically for this design, we actually work with 5-pole Chebyshev low-pass prototype with a 0.1 dB passband ripple. Okay, the low-pass prototype parameters. Okay, so basically you can get all these parameters from the table easily. Okay, the bandpass filter is designed to have a 15% fractional bandwidth. So basically, as compared to the previous example, okay, we actually tweak this instead of 10%, we tweak it to 15% bandwidth or FBW 0.15 at a mid-band frequency of F0 equals to 2 GHz. Okay, so basically these are all the formula which I have shown it to you early on. Okay, so these are all the set of formula. So from here you can calculate the QE1 and QE5. Okay, so basically QE1 and QE5 will be the input and the output here. So basically this will be the so-called the QE1, okay, and also the QE5 for the input and also the output. M12 and M45, okay, so this part here will be the M12, this part here will be the M45. They will be the same because this filter will be symmetric. And M23 will be the same as M34, okay, this part here will be M34. This part here, this part here will be M23, this part here will be M34. They will be the same because the filter need to be symmetric. And how to calculate, okay, so basically I have shared with you the formula on the previous page. Basically, you just enter the parameters. For example, G0, okay, basically is 1. Okay, G1, which is 1.1468. Okay, fractional bandwidth, which is 0.15. So you just need to punch your calculator. I don't foresee you have any issue to get this number, 7.645. Same for this M12 and M45. This is a fractional bandwidth, which is 0.15. Okay, you actually has this square root G1. So G1 is 1.1468 here. G2 is actually 1.3712. Again, you punch your calculator, you should be able to get this 0.1196. Okay, same for M23 and M35, M34. Okay, so these are the formula. Okay, so FBW is 0.15, G2, okay, which is 1.3712 here, G3, which is 1.975. So again, you punch your calculator, okay, you should be able to arrive this answer, 0.0912. Okay, so basically next. Okay, so next is this is the so-called the table for external quality factor. Okay, so I will put the link how we actually can have this graph. Okay, so basically this graph, you need the help of simulation in order to get this graph. Okay, but once we actually get this graph, it will be much more easier. Okay, so basically this is for the input and output. Okay, so therefore these are known as external quality factor QE. Okay, so basically this is the location, okay, on the input. Okay, so basically I will mention a little bit more, but remember earlier on I mentioned that we also need to control the location of the input and also the output. Okay, so basically earlier on we have calculated the external, so this part here, QE1 and QE5, this is actually to determine the location, okay, on the external quality factor. So basically we have this 7.645. So you just need to find this 7.645. Okay, so basically this is 7, roughly around here, which is 7.645. So from here, we calculate that the T distance, okay, which will be 3.75 millimeter here. So once we done this, we are ready to calculate the coupling coefficient. Okay, so there are actually two sets of coupling coefficient. So first one will be M12 and M45. Earlier on, we have calculated that this is actually equals to 0.1196. Okay, so basically over here, you can see that this is roughly about 0.1196. So from here, we can see that the gaps in between the resonator will be 0.58 mm. Okay, so this M23 and M34, they are the same, which we have calculated earlier on, which is 0.0912. Roughly, okay, this is actually where is 0.0912. And from here, you can see that this is 1.5, 1.6, 1.7. So over here is roughly about 1.71. Okay, so basically this is actually the so-called the spacing, okay, between the resonator. Okay, again, I like to say a few words how we actually get this graph is basically you run a so-called simulation. Okay, but don't worry, okay, I will put the video that actually design this so-called external quality factor here and also this coupling coefficient, how we actually can plot this line here. Okay, I will put that particular video, okay, on to the description. Okay, so basically, if you are not sure how I actually plot this graph, take a look on that particular video, okay, run some simulation, and you will be able to arrive this graph. Okay, so basically, what I have done over here, okay, I have done the distance, which is 3.75 mm. I have also done the gaps in between the resonator. Okay, for M12 and M45, the gap basically will be 0.58, and for the gap of M23 and M34, the gap will be equals to 1.71 mm. Okay, so basically with all these things, I'm ready, okay, to design the pseudo-combline filter. Okay, so basically I have mentioned this is basically this is so-called without the capacitor. Okay, so these are all half of wavelength. Okay, so basically half of wavelength, which means that lambda G over 2. So basically this will be the length. Okay, so we need to keep certain thing same. Okay, as you can see for the example here. Okay, so what we keep the same, okay, basically we fix the line width for all the resonator as 0.8 mm. Okay, so basically for the tap line, okay, they need to be 1.1 mm because this 1.1 mm basically will be a port of 50 ohm. So basically, once you have this, you know over here, okay, this part here will be 1.1. Okay, so basically this part here, we need to fix at 1.1 because this part we want to ensure will be a 50 ohm. So this part in short will be a 50 ohm so-called transmission line under microstrip line. So basically this is for the so-called the input, and this will be for the output. They will be the same. The strip line, the microstrip line will be 1.1 mm. Okay, so as for the rest of the microstrip line, they will have a width of 0.8. So basically, in short, all these microstrip line, they have the width of 0.8. We make it all uniform so that will be much more easier. Okay, so basically, let's come to the design. So basically, we have so-called done this early on with 3.75. Okay, so basically, it's a spacing between the center. So you actually have the lambda over 2. So basically, this will be the center. Whatever the difference, you will be adjust from here, which means that this part will have some of the different. This part here basically will have a quarter wavelength. This part will be so-called virtual short circuit over here. Okay, so basically we have calculated earlier on, which is about 3.75. Okay, so basically you can see that I actually put at the length of 3.8. Okay, so basically 3.8 mm. This is where the feed line position is supposed to be at the middle of this. Okay, versus the middle of this half of wavelength. Okay, so basically with a spacing of about 3.75, or maybe I actually make it easier to be at 3.8. So basically this will be the input port here. So next, okay, in terms of so-called the spacing here. So the first one, okay, which is 0.58. So basically you can see over here, this is actually 0.58. Okay, so basically this is the so-called coupling coefficient between the resonator. So this will be also same as 0.58 here. So next one will be actually equals to 1.71, which is here. This part here will be 1.71, same as this part here, which is 1.71. Okay, so with this, you can see that I have successfully designed the pseudo-combline filter. So basically, you just need to control a few parameters. Okay, firstly, where will be the location of the input and also the output port? They are symmetric. So basically, from this graph here, you actually know the spacing, which is with reference to the so-called the center line, okay, of this half of wavelength resonator. Next, okay, within the resonator, what will be the spacing actually will be determined from this graph here. So the first one I have found, which is 0.58 mm, this part here, and will be symmetric. This part also will be 0.58. The next one will be 1.71, okay, which means that this part has the spacing of 1.71, same as this part here, which is the spacing of 1.71. So from here, you can see that I can easily design this pseudo-combline filter. Okay, so let's come to the frequency response. Okay, so basically, remember, we are tasked to design a bandpass filter, okay, center at 2. Okay, so basically you can see that I have successfully done this. Okay, so this is actually quite similar with the combline filter. There is an attenuation pole near the high edge of passband. Okay, so basically on the upper side, there is actually a so-called attenuation pole. Okay, which means that we actually have a better so-called frequency response on the higher side. So basically, it will be the same as the Combline filter. Okay, so on the part 35 series discussion, I have also showed the frequency response. They also have this attenuation pole near the high edge of the passband here. Okay, so this actually result in a higher selectivity on that side. Okay, so this attenuation pole is likely to be due to cross-coupling between the non-adjacent resonator. However, okay, with the second passband, okay, so basically you can see that this is actually the second passband of the Pseudo-Combline filter is centered at around 4 gigahertz, okay, which is only twice the mid-band frequency. Okay, so this is expected, okay, because the lambda over 2 resonator are used without any lump capacitor loading. Okay, so basically these are undesired. We actually have another passband, okay, which is about 2 times from the design, which is 2. So we have another passband at 4. So basically, with this, I'd like to end my discussion. Okay, in this video, I have discussed firstly what is the key difference between pseudo-Combline filter and also Combline filter. Next, okay, I show the design. How can we actually design this pseudo-Combline filter? And basically with this example, I think this is quite clear. How can we actually design a pseudo-Combline bandpass filter? With this, that's all. Thank you so much. Once again, I'd like to see you guys soon. Bye-bye.